Hi there, welcome back to this channel. In this video, we are going to be talking about the special relativity. More formally, we call it Einstein's special relativity. Okay, now, to begin with, let us talk about classic physics, versus relativity. Okay, now Newton's laws, that is, when we talk about classic physics, we refer to or classic mechanics. So the Newton's laws, they work perfectly. The Newton's laws of motion, Newton's laws of mechanics generally, they work perfectly when we are dealing with everyday speeds, like the speed of a moving car. For example, speed of a moving car, or the speed of planes, or with people walking, generally people walking, or objects falling from a height, etc. But when objects now start to move at speeds that are close to the speed of light, Newton's laws don't give accurate results anymore. Newton's laws are not applicable to objects, unapplicable to objects that are moving at near speed of light. And the word is, what I said here, near speed of light, is very important because we know that objects cannot move at speed of light, only at near speed of light. Objects that have mass cannot move at speed of light. Now put that in mind. So we know that when we deal with objects, it comes to happen that objects that move at near speed of light, with such objects, the Newton's laws do not give us the exact or accurate results. Now, that's where relativity now comes in. So here's where relativity comes in. Now, relativity comes in to give us the right answer. So, for example, if you are tossing a ball on a moving bus, so let's say you're tossing a ball on a moving car, for example. Now, Newton's laws explain everything well. But if that bus were to be moving at near speed of light, now you are inside this bus, and now we're assuming, now we know that that is not possible. Is that okay in reality? That the bus cannot move at speed of light. But let's just try to imagine that if that bus could move at speed of light, or near speed of light, near speed of light. Now you start to see things, something strange happen, which is different from what Newton's Newtonian mechanics explain. Is that okay? Now, what happens is that you will begin to see that time slows down. Time slows down for the person in the bus, the person moving at that same speed. Time slows down. So that's where Einstein's special relativity becomes very necessary. It explains how that time can slow down for objects moving at near speed of light. Now, the theory of relativity basically is based on what is called inertial. We call it inertial frame of reference, or inertial reference frame. Is that okay? Inertial frame of reference. This is what the principle of Einstein's special relativity is based upon. Inertial frame of reference. All right. So first, let's explain the term, the meaning of frame of reference. Now, a reference frame, or a frame of reference, basically is a coordinate system. This guy is basically what? A coordinate system that is relative to which physical measurements are taken. So coordinate system is a coordinate system. The frame of reference is a coordinate system relative to which we can take physical measurements. So that basically means that it is a particular thing that we take measurements of physical quantities relative to. Is that okay? So now a natural frame of reference is now one. So if you call it inertia, basically first let's understand what inertia. Inertia means an object that is, inertia simply comes from the word that means lazy. Is that okay? Lazy. All right. So inertia means has no acceleration whatsoever. The body is not acceleration, or the body is moving. You say the body is in inertia if it's moving with uniform velocity. Uniform velocity, when the body is not changing velocity. So basically, change in velocity is acceleration, so the body is not accelerating. So now, an inertial frame of reference, therefore, let's call it inertial, IFR, inertial frame of reference. Now, inertial frame of reference would therefore be the one that moves with constant velocity. Is that okay? Or that is not accelerating at all. A frame of reference that we want to use to make measurement of a physical quantity that is not moving. So it means the frame is not moving. Is that okay? Or the frame is moving at a uniform speed. Okay. Now that said, let's come to understand the special theory of relativity. Let's try to understand the special theory of relativity. Now, it was proposed, first understand that it was proposed by Albert Einstein in 1904 to 1905. Some sources have it as 1904. Some sources say it's 1905. But basically, I think it's 1905. And, it's concerned with bodies. It's concerned with bodies that are moving with constant velocity. Is that okay? Or bodies that are not accelerating. Is that okay? So that's the special theory is concerned with that. Now, that theory is predicated on two postulates. So there are two postulates. And the first one says that the laws of physics are the same in all inertial frame of reference. Is that okay? Let me put that down. The laws of physics are the same in all inertial reference frames. Is that okay? Reference frames. Okay, IFR, in all inertial frame of reference. Let's put it that way. Inertial frame of reference. Okay. So, and therefore all motion will be what? Relative. All motion will be relative, since the laws of physics are the same in all inertial frame of reference. So, and what that means is that the velocity of an object can only be given relative to another object. So the velocity of body will be accounted for relative to another object. Is that okay? So more like we cannot really calculate the velocity of that body itself, only relative to us or relative to another body that is moving, that is at inertia. Is that okay? That is at inertia rather. So that is what that law is saying. So the laws of physics are the same in all inertial frame of reference. That's very simple. The laws of physics are the same in all inertial frame of reference. Now the second one is the postulate of the speed of light. The speed of light postulate. Now, the speed of light postulate. Now this one states that the speed of light we represent that with c. Is that okay? The speed of light c in free space or vacuum, you could see vacuum in your textbook, in free space or vacuum, has the same value for any observer or all observers. Is that okay? For any observer, independent of the motion of the source or the motion of the observer. Is that okay? So regardless of the motion of the observer, the speed of light measured in free space or in a vacuum is always the same. That's the second postulate. So there are two postulates. The laws of physics are the same in all the inertial frame of reference. And the second is that the speed of light. Now let's hold these two postulates at heart, because it's going to dictate how we understand the theory, the special theory, theory of relativity. So he says that the speed of light postulate is that the speed of light is always the same for all observer, independent of the motion of the observer or the motion of the source that is measuring it. Is that okay? Now, one thing you should now know is that the classical concept of time, or Newtonian concept of time, the Newtonian concept of length, that of momentum, of energy, kinetic energy basically, and addition of velocities, those are the primary ones that this theory of relativity tends to really affect. And of course, they also affect the shape of the universe. And we're going to get to that in other videos. But basically, now this concept, this classical physics, this concept of Newtonian concepts are not wrong. Is that okay? They are not exactly wrong. Now, the only thing is that they are limited to speeds that are very small compared to c, compared to the speed of light. Is that okay? So in fact, we represent their own velocity with v, and represent the velocity of light with c. So we say this theory only applies, the classical theory only applies to v, which is less than c. So this double less than means very, very less than. That's mean this double less than, it means very less than. Is that okay? So we know that these theories, Newtonian mechanics, is true only when the bodies are moving at speeds that are very, very less compared to this. For example, a body moving at the speed of 38 kilometers per hour, or 40 kilometers per hour, or even 120 kilometers per hour, that is very, very small compared to the speed of light. The speed of light is about 3 times 10 raised to power, approximately 3 times 10 raised to power 8 meters per second. Is around 297 something. So very, you see how this is about 300 million meters per second compared to 120 kilometers per hour. All right, so that is the those are the two postulates. And so I only first clarified here now that those theories that classical physics hold are not exactly, they are not wrong. They only apply to velocities that are very, very much less than that of the speed of light. So the relativistic view is, it only applies to speed that are the relativistic view, so to speak, applies to speeds that are between 0 and speed of light, and that is why it's a more accurate measure. Is that okay? So we only see it as a more accurate measure, but those ones, the classical mechanics, viewpoint of speed, of time, of all of those things are not exactly wrong. Okay, I hope that is clear. Now, let's talk about relativistic view of time. So now we have the relativity of time. Relativity of time is also called time dilation. Relativity of time, or time dilation. So now, the word dilation primarily means expansion, or basically means expansion. Dilation means what? Expansion. So what are we saying in essence? We are trying to say in essence that time is going to expand. Is that okay? Time is going to expand. Now, let me explain what that says, what that is about. Now, what does this time dilation practically mean? We said this one means expansion, right? Okay. Now, what it basically means is that time can pass at different rates for any two people, provided that one is moving very, very fast. Usually we say at near speed of light. So when I'm talking about speed now, I'm referring to speeds that are near speed of light. Okay, so I'm saying that when time dilation is explaining the fact that time passes at different rates. That's what it's saying. For people or objects, for moving object, for objects that are moving relative to each other. Is that okay? Where one is very fast for moving objects. When I say for moving objects, I'm talking about objects that are moving near speed of light. So now, for example, let's say there are two people. Now, one is on Earth. Is that okay? One is on the surface of the Earth. So let's put the surface of the Earth here, for example. So this is the surface of the Earth, and there is an observer here. So there's an observer on the surface of the Earth. Okay, so this is our observer on the surface of the Earth. And there's another person, an astronaut, that is in a fast-moving spacecraft. So let's say it was in a fast-moving spacecraft. So let's draw a spacecraft here. Just manage my drawing here. So let's say this was a fast-moving spacecraft. So this is our astronaut here. Our astronaut is, putting on the gear, the, astronaut gear. Now, so there's one observer here, there's another observer here. Now, and let's say both of them had a clock that was visible to both of them. Let's say the clock, so the clock is in this fast-moving object. Is that okay? So this object is moving very fast, as I was saying, and there's a fast-moving clock here. Now, according to Einstein, this person on Earth will see the astronaut's clock. Now, we are assuming that both of them can see the clock move, can see the clock. The clock is visible to both of them. So this person here is going to see the astronaut's clock ticking slower than our own clock. If they had clocks, both of them had clocks that are visible to both of them, this person that is in the moving gear he is going to see his own clock at the normal rate. He's going to see its own clock ticking the normal way it should tick. But this observer is going to see the astronaut's clock ticking slower than her own. Now let me explain how the clock works. Now imagine that we have a light clock that works with a beam of light. So, and the design is such that there is, so let's say we had something like this, a structure like this, and a light source at somewhere here. Now this from here to here is so close to each other. Is that okay? The distance is not much. So the distance between here and here, let's call it D. Is that okay? Now, so this guy is a light source, light emitting source. So by the time it produces light wave, it's going to strike this object and come back to a detector. Is that okay? Now a detector. So it means that the distance traveled by this light is going to be 2D. Does that make sense? 2D, that's the distance traveled by the light. And the moment it strikes this detector, let's call it our 1 second. Is that okay? As the light will go up from this metal, this light emitting source, and strike this. Okay, let's call it a mirror. Let's call this a mirror. Is that okay? Since the reflecting surface. So now when it touches the mirror and bounces back down, so that's a tick. That's a tick for the detector. Is that okay? So every time the light makes this round trip like this, it counts as 1 second. Now, the astronauts will see the light going straight up. This astronaut, so this thing is basically inside this place. So let's just draw it here. The light is going up and coming down. That's our light, that is our clock. Oh. Is that okay? This is our light clock. Yes, let's call it the light clock. Let's call it the light clock. And I hope you understand my diagram. This is our aircraft, our spacecraft, and this is our astronaut. Okay? Now, the astronaut will see this light go straight up and come down. Is that okay? Because it's inside the spacecraft, so it will be seen only upward and downward movement of the light. Is that okay? But the person on Earth, so we say that is in his own, so he's going to be seeing 2D. Does that make sense now? It's going to be seeing 2D. And distance, remember that speed is equal to distance over time. So it means that distance is equal to what? Speed times time. In this case now, we have two types of time because we are talking about time dilation now. Speed here is going to be the speed of this light. Does that make sense? I said distance here, which is our 2D here in this case, is going to be equal to speed of light times the velocity of the body. Speed of the body rather, which is the velocity of light, times the change in time T naught. Now let's call T naught, change in time naught, the proper time. We want to measure how this time changes relative to each of the observers. Is that okay? So this first observer is going to have see this 2D at C times change in time. And this time is called the proper time, the normal time. How this is clear, I did not invent any equation. Look at it, the distance is 2D. The distance is, and it's 2D that this guy will see. The first D, upward direction, the second D, downward direction. So two distances, that's 2D. So I know that distance is equal to, by the time you, speed is equal to, we say speed or velocity. Velocity is equal to distance over time. Velocity is displacement rather over time. So since velocity is displacement over time, then distance or displacement, therefore, will be what? The speed times time. Okay. So we said, so this equation holds true for the body, for the astronaut. So 2D is equal to C delta T naught. So this change in time, because we are measuring the change, the change in time that over which that event is occurring, the flash of light. Now, however, this person on Earth is going to see the light moving in a diagonal zigzag path. Let me draw what that means. So this guy is on the whatever, on the surface of the this guy is on the, these are our astronauts. Is that okay? So, and the body is, the astronaut is traveling. Now what this guy will see, so these are surface of the Earth again. Now what this guy will see is that since this guy is traveling straight up like this, now what this guy will see is somewhat like this. Now watch me. These I'm drawing here is our spacecraft. Is that okay? So what this guy will see, what this Earth observer rather will see is he will see only the first movement of the light from the source. He will see it move from here, because this guy, first understand the fact that this spacecraft is traveling at near speed of light. How that is clear. This spacecraft is traveling at near speed of light. So V is the velocity of the aircraft now, is less than C, but you see it's not very less than C now. You see I'm putting one less than. Is that okay? Okay. Now, so because it is moving at near speed of light, before he sees the light touch this mirror, he's going to come, the aircraft might have made its way here, so he's going to see something that looks like this. So this is the light going to hit, let me use a red bar for that. So the flash of our light, this light flash will come to hit the metal detector at this point, and the moment, and you know it's going to return, right? It's a two-way movement. The moment it will be coming back, the aircraft might have gotten here, and the light will now come to be hitting this guy here. Will now come to be hitting the observer, the detector rather here. That is the two-way movement of the light now. Because this aircraft is moving, let me explain that. This aircraft is moving, spacecraft rather, is moving very fast. So because it's moving very fast, this light source is going to, before the light hits the mirror, the spacecraft will have gotten here, and this guy, the light will just be hitting the mirror, and before the mirror will reflect it back to the detector, the spacecraft will have gotten here. So you now see that the movement of the guy now, I want to use different colors. So the movement of our guy, the movement of our light, as the movement of the aircraft first is from here to this place, right? So so this place, let's divide it into two distances. Let's call this distance L, let's call this second distance L. And let's call this this difference in this distance here S, and let's call this distance here small s. Does that make sense to you? Now, if we wanted to get the value of this distance S, that is the distance that the light has moved Kind of. You know that in this place, the distance the light moved is just d. And now 2d because it's a two-way movement. In this case, the light has moved a distance, a stretch in distance, so we are calling it s, no longer d. I hope that is clear. We are calling this place 2s, no longer d. So s here, so we can create a right angle triangle, a vector diagram here that will look like this. So here becomes the L and here becomes S. I hope that is clear. Okay. All right. And you know that from here to here, which is basically where we are studying, from here to here is the distance, the normal distance that the guy is supposed to move, which is d. The distance for the light. Is that okay? That's d. Okay. That's where the guy is supposed to move. But now, because of the movement of the aircraft, the distance has the light has moved from here to this point, and has also moved from here to this point. Okay. Now, if we wanted to calculate the distance that the light has now moved, let's call that s. S will be equal to s squared. Do you remember Pythagoras theorem? Hypotenuse is equal to opposite square. Let's say theta was the opposite square plus adjacent square. So d squared plus l squared. So that now s will be equal to d squared plus square root of d squared plus l squared. Okay, I hope this is clear. Now, now. Okay. Now you know that there are two distances it's moved to. It moved up and down. Okay, so we'll say 2s therefore will mean what? 2 times of these guys. Does that make sense? Since our guy moved from here, the light moved from here to here, 2 distances 2s. So 2s means if s is this, then 2s will mean 2 times the square root of d squared plus l squared. But there's something we did not also talk about. Now, time would have expanded here in this case, because so the expanded time here is going to be, you know that velocity is equal to distance over time. So time therefore will be equal to distance or displacement over velocity. Okay, so if that be the case, then it means that for this our case here, the distance moved here is going to be what? L for the aircraft. So we are talking about the aircraft. The aircraft is moving with the astronaut. So the astronaut is going to see a dilation in time, which we call delta t. Remember, delta t naught is the original time that the astronaut sees inside the guy. But the time measured by this observer of this astronaut is going to be a dilation in time, which is delta t. And delta t in this case is going to be distance, which is LL, which is 2L over the velocity v. Does that make sense? Over velocity v. However, the light itself has moved 2s, right? That is 2 distance, which is equal to what? Which is equal to c delta t. So let's here is 2d. That is what this guy is saying. So in real time, actually this is what is happening. But with respect to what is happening here, this guy sees light to have traveled 2s, which will be equal to what? C delta t. Okay, but he sees the astronaut to have traveled 2L, which is equal to v delta t. I just revised this equation here. So let's call this equation 1. Everything here. Let's call everything here equation 1. And let's call all our equations. No, let's call this one equation 2. And let's call our equations here equation 3. Okay. Now let's go for that. Then let's call this one equation 4. Recall how we got this. So we have known now that 2s is equal to, from here, 2s is equal to 2 d squared. Okay. 2s is equal to 2 roots d squared plus l squared. Okay. Now we know how we got all of this. Let me bring all our formulas here. So we have 2d equal to c delta t naught, and we have 2s, we have 2l equal to v delta t. This is the dilation in time, and we know that 2s also is equal to what? C delta t. And this dilation in time is also what? 2l over v. Now, one thing we can begin to do here is we can substitute. If we want to calculate, now we know that 2s, if we want to calculate the dilation in time, this equation has what the dilation in time, it contains the dilation in time, that's delta t. Okay, so we call this delta t the dilated time interval. So delta t is the dilated time interval. Okay, so del 2s will be equal to c delta t, which is equal to what? 2 roots d squared plus l squared. Now l here, let's substitute for l here, because 2l is equal to v delta t. So l will be equal to L will be equal to V delta T over 2. Does that make sense? L will be equal to 2 because 2 takes care of 2 here. So that C delta T will be equal to 2. Excuse me. Give me water, please. So you know that. Let me pause it, please. Okay, so we said that C delta T is going to be equal to 2 root d squared. Now we know that L is now V delta T over 2, so we have V delta T over 2. Now L is squared here, so all of this carries squared. Okay, so we have something that looks like this. So we have C delta T to be equal to 2 times the square root of d squared plus v squared delta t squared over 4. Okay, we can make sense of this. Now, one thing we can do from here is to, we could square both sides. If we square both sides of the equation to remove this square root, because you can see that the reason why we're doing that is because there is dilated time interval here and there's dilated time interval here. And what we are trying to derive is the equation of dilated time interval. So if we square both sides, then we'll have that c squared delta t squared is equal to 2 squared times, now root would have gone, then we have d squared plus v squared delta t squared over 4. Okay, that's how we square both sides. This takes care of this, and then this is squared. Okay, so now from there we can now have that this guy is going to open this bracket, so that when he opens the bracket, we're going to have c squared delta t squared is equal to 4. Here's 4, right? 4. Now, okay, let's open the bracket with 4. So we have 4d squared plus v squared delta t squared over 4. Okay, so we now open the bracket with 4, and we have c squared delta t squared is equal to 4d squared plus 4 times v squared delta t squared. I'm trying to be expressive so that you can understand what is going on. 4 takes care of 4. So we have c squared delta t squared is equal to 4d squared plus v squared delta t squared. Okay, now if this is the case, we want to get the time dilation together. So this guy will come here. So we have c dilated time interval. This guy will come here, c delta t squared minus v squared delta t squared delta. Okay, is equal to, I hope it's clear, 4d squared. So by doing this, we have collected delta t squared together. So we're going to factorize that. Delta t squared is common between, by the time we take care of this delta t squared, to remain what? C squared minus, we take care of this, it remains what? V squared is equal to 4d squared. Okay, now from here we can divide both sides by these guys to make this guy stand alone. So we have c squared minus v squared, c squared minus v squared. So delta t squared, watch me, will be equal to 4d squared over c squared minus v squared. From here we can take the square root of both sides. Is that okay? When we take square root of both sides, cancel square here, and we have delta t will be equal to, take square root of this place. Square root of 4 is 2, square root of d v squared is d all over square root of c squared minus v squared. Now don't make the mistake of taking square root of this and square root of this, because you have to take this. The square root should cover both of them, so this remains valid. Is that okay? 2d over what? 2d over c squared minus v squared. Now from here, one thing we can do is this. Do you remember that okay, look at this. Okay, look at this. We have 2d is equal to c delta t naught. Does that make sense? So it means that from here, that delta t naught, which is the proper time, is equal to 2d over c. Okay, if that be the case, then it means that 2d here, 2d in this case, our 2d in this case is going to be c delta t naught. Oh, okay, yes. So we can just use this directly. Does that make sense? Since 2d is c delta t naught, 2d is c delta t naught. So we have that delta t is equal to c delta t naught. 2d is equal to what? C delta t naught. I hope you got how. Now, if you don't understand how I got all this equation, you have to revise it. Is that okay? Revise all what I did. So, c delta t naught over the square root of this thing of c squared minus v squared. Okay. Now, if we have this, we can, let's do some manipulation here. We can divide through. Let's divide through by c squared, or by c. Let's divide through by c. So let's divide through by c. Divide through by c. So by dividing through by c, we are going to have no on this side or only on this side. Is that okay? We want to divide through by c only on this side, and it will not affect it. Is that okay? So we're going to have delta t equal to c delta t naught over c. Is that okay? Times, you know, this expression here is 1 over root c squared minus v squared, and I've not changed anything. So now in the same way, I'll divide these expressions themselves using c. I'll divide them by c. Or no, let's use c squared actually. If you use c squared to divide through, that's when this guy can have squared. All right, because I remember the equation. Is that okay? So you use c squared, you divide through by c squared here, divide through by c squared. So if you divide through by c squared, then c here 1 to remain 1c down here, then in this place c squared takes care of c squared, then you now have delta t will be equal to what? Delta t naught times 1 over root. Now here we have, these are taking care of this, so we have 1 minus v squared. Yes. So this is the formula for the dilation in time is going to be equal to what? Delta t naught all over root 1 minus v squared over c squared. And that is the formula. So this is the formula for dilation in time. Okay, it's nothing hard at all. Just follow this series throughout. Follow all that I tried to do from the beginning to the end. You're going to get how to derive it. I'm trying to show everything again. So follow it all through like this. And you're going to get how to derive the equation for the fundamental, the dilation in time. So you see, that is quite easy, yeah? That is quite easy. Now, so what this is saying at the end of the day is that even though the light is moving at the same speed for both observers, according to this theory, that the speed of light postulates that the speed of light in free space has the same value for all the observers, regardless of how their position of measurement. Now, even though that is the case, according to second theory, now the diagonal path that light has taken, it has made light to it traveled that path in the same at the same speed. Is that okay? But it has covered a longer distance. So because it's covered a longer distance, it means that time has more time has passed for this person on earth. I don't know if that is clear. As in that it traveled this diagonal path that the light took. It took that path at the same speed, but because it covered a longer distance, now it covered a longer distance L to L here, then it means that more time would have passed from the Earth's observer's point of view. So his own point of view, from his own point of view, that's the person observing on Earth. From his own point of view, more time would have passed. Is that okay? More time would have passed. Now, the ideal idea is that this astronaut is going to feel time is normal. Is that okay? Because his clock will be ticking normally. But the Earth observers, this Earth observer will see the astronaut's clock running slowly. Is that okay? And that's time dilation. That's time dilation. So basically in 1971, these two scientists, J.C. Haffel and R.E.J.C. sorry, trying to be fast. J.C. Haffel and R.E. Keating, actually. How's the spelling? I think it's this. Let me check this spelling is great. Okay, but I think so. It's R.E. Keating. They proved. Yes, thank you. So R.E. Keating, both of them proved the fact that time dilation actually existed. More like they confirmed the theory of time dilation. They confirmed the theory of time dilation. Now let's get to the next aspect of this. Now, which is length, relativity of length. Now this is what I'll try to do. Relativity of length. Now that equation that appeared on the thumbnail. Now here's what we're trying to do. I want to try to be fast so that I can show you that equation, the derivation of that equation that appeared on the thumbnail. Okay. Now let's talk about the relativity of length. Now, relativity of length is also called length contraction. It's also called length contraction. Hold this thing. Length contraction. Okay. Now, what is length contraction? Now, generally, when we measure the length of objects, it does not depend on who is measuring it. The length is always constant. Is that okay? The person that is measuring it is not, the length of an object is not subjective to the person that is measuring it. Okay. Now that is clear. Now, if that be the case, what that is saying, for example, is that if a stick is actually 1 meter long, whether it is lying on a table or standing straight or flowing through the air or whatever, it is going to be exactly 1 meter all the time. Is that okay? But when it begins to move at a speed that is close to that of speed of light, then something strange occurs again. Is that okay? Now, as close to speed of light, the length will depend on the motion of special relativity. Is that okay? Now, the length will now depend on the motion. Is that okay? Now, when that object is moving at near speed of light, now relative to you, if you are stationary, for example, that object is going to appear shorter along the direction of motion. Does that make sense? It's going to appear shorter along the path of motion. Okay, what that means is that if it's at rest, for example, for a body that is for a 1 meter long ruler, for example, let's say you were standing on a platform. So this is you, your small head, or maybe your big head, is standing on the platform, and a super fast train rushes past you near speed of light, which is impossible basically. So a very fast car or train or whatever, an object that is moving very fast, and is inside that object you have your ruler. That's my point. Now the ruler is inside the object. The ruler that is 1 meter, you have measured it to be 1 meter or 1 meter long normally. So if it's inside this object that is moving very close, very close to speed of light, inside this train or inside this car or inside whatever, this rod is inside this whatever. This rod is still 1 meter long. Now, but to someone that is sitting on the train, I mean, for if you are sitting here now on the train, you will be measuring it at 1 meter this rod will still be 1 meter long. But for you, and this guy is whooshing past at, he's whooshing past you at near speed of light, very fast. Okay, so you that you are on the platform, the rod will look shorter, maybe about 60 centimeters. Is that okay? That's 0.6 meters. Maybe something like that. So that shrinking in length that you experience, because you are seeing it pass so fast, are seeing it move fast. You see, my hand is moving at near speed of light. So that contraction in length, or shrinking in length, is called what? Length contraction. Do you understand? Shrink in length or contraction in length. Now, what causes it is this. According to Einstein, we know already that time slows down for moving observers. Is that okay? So if that is time dilation, basically, that's what I just used again as an example. So if time is slowing down, you know that space and time are linked. Is that okay? In what Albert Einstein called space-time. Is that okay? Space-time. I'm going to explain that in another video. Maybe I'll release the video on, maybe I'll release immediately after this one. Space-time, about space-time. Now, so he said, and the idea is that time slows down for a moving body that is moving at near speed of light. Time slows down. We have established that, right? And we explained that the dilation in time is equal to 1 dt naught over root 1 minus v squared over c squared. Okay. Yes. Okay. So if this is the case, now the change in time for the proper change in time for the guy inside this place is because it's measuring that proper time, the length, what he will see is L over the speed. Now this L naught, which is the original length, this L naught is because of now this V is the speed of the train, which he inside the train is also moving at. Does that make sense? But for the observer on the platform, this guy, we'll measure L, which is the length contraction, over V. Does that make sense now? Now, the V is constant because both of them are seeing the velocity of the train, of the moving train. Okay. Now this is the case. Let's substitute this into the equation. You know, therefore, that from here, delta t naught is this, okay? So that becomes, if delta t is this, delta t, which is interval of dilated time interval. So we have L over V will be equal to, here is delta t naught, that will be L naught over V times 1 over root. How is the case? You know that 1 minus V squared over C squared, is that the case? No, or this guy is going to measure dt naught is equal to L over V, while dt is equal to L naught. I'm trying to remember how to prove this. Is that okay? This is okay. So if that's the case, then delta t will be L naught over V. Okay, L naught over V. Oh yeah. I'm sorry. Yes, that's the idea. That delta t naught is going to be L over V, which is the original length of the rod divided by V. That is the contracted length of the rod. Okay, this, so who is now seen at proper time? The person seen at proper time is this person, and the person seen at contracted length, or dilated time rather, is this person. Okay. Okay, yes. This, okay, yes. So, okay, now this person now is seen at original length. Is seen, no, is seen at the proper time. Does that make sense? Is seen as the at the proper time. Okay, so proper time is going to be equal to the length, contracted length over V. While the person that is on this platform will be seen at a contracted, a dilated time. He will be seen at a dilated time, and he will be seen L naught over V. Okay, that's the idea. So that by the time we substitute this for T naught, L over V, and for T, change in T, L naught over V. So change in T will be L naught over V equal to delta T naught will be L over V times 1 over root 1 minus V squared over C squared. Okay. So if that's the case, I'm sorry for the mistake. If that's the case, then V takes care of V. Is that okay? I mean, if you multiply by V, multiply both sides by V, V will take care of V. Okay. So L naught will now be equal to what? L over root 1 minus V squared over C squared. Okay. While this L is actually the contracted time, contracted length. Does that make sense now? This L is the contracted length, so we have that L, I think we cross multiply, L will be equal to L naught, this is the formula, minus V squared over C squared. Alright, so this is the formula for length contraction. L naught is the proper length. Is that okay? The actual length of the rod. Now, the second to the last we'll be observing is the relativistic momentum. Is that okay? Or relativity of momentum. Now, I will not be deriving anything here. Just the idea is that for an object that is moving close to speed of light, now the momentum is different from that is moving from the normal momentum of object that is moving at V. For normal momentum of object moving at V, we say is mv. But for momentum of object moving at near speed of light, it will be given as mv over this over root 1 minus V squared over C squared. So this is momentum of an object that's moving near speed of light. And the reason is because at very high speed, the mass, so we said that at very high speeds, and when I mean high speed, what I mean near speed of light. Is that okay? Mass seems to increase. Is that okay? And that's due to relativity. Is that okay? So, and to the observer, relative to the observer, the time will seem to increase, and so because of that, the momentum that is felt is mv over this. Is that okay? Now let's talk about total energy in relativity. Now I'm going to be deriving the equation for total energy in relativity also, so that'll be the last thing we'll be deriving. Is that okay? The video is already too long. That's 53 minutes. Jesus Christ. Okay, so now for Albert Einstein in 1904 had already shown that the mass and energy are interconvertible. Is that okay? That the mass of a body is highly proportional to the mass of the body. The higher the mass, the higher the energy of the body. Is that okay? So when the body adds mass, the body adds energy. And he proved that with his famous equation E equal to mc squared. Is that okay? And we call this E the binding energy. We'll be seeing that in nuclear chemistry. Binding energy. Is that okay? Is the binding energy, which is basically the energy that is required for all the atoms that are inside a particular substance to hold each other together. Is that okay? But this case is in the resting stage, or the resting state of matter. The resting state. Matter in the resting state only has E equal to mc squared. When a body, so at this place we say that velocity is equal to 0. Is that okay? But when a body is accelerated from rest, now it's going to gain a kinetic energy. I hope that is clear. When the body is accelerated from rest, it's going to gain kinetic energy. So the total energy of the body is going to be what? The kinetic energy plus so let's call this E sub naught, which is the minimum energy, the lowest energy of a body, which is the energy of a resting body. So E, Ke plus what? E sub naught. Now, according to relativity, the energy of a moving body, the total energy of a moving body is going to be what? mc squared over the same thing. Does that make sense now? Over root 1 minus v squared over c squared. Okay, so if that be the case, then if E is equal to this, then Ke will be equal to what? Energy minus E sub naught. Does that make sense? So we have E will be equal to what? Ke, rather, kinetic energy will be equal to mc squared, because this E, mc squared over root 1 minus v squared over c squared minus E naught, which is mc squared. So mc squared is common. So let's factorize that. We have Ke will be equal to mc squared is common between 1 over root 1 minus v squared over c squared minus, if we factorize this guy, if we take mc squared out, to remain 1 here. So this is the equation for kinetic energy. Okay, now let's now deal with the relationship between the total energy and momentum. So that equation you saw down is an equation that you saw on the thumbnail, rather, is the equation that shows the relationship between momentum and total energy. So let's recall first that we said momentum is mv over 1 minus, okay, over 1 minus v squared over c squared. So this is the case for momentum of a fast moving body. And we also recall that E, we said total energy is going to be mc squared over the square root of 1 minus v squared over c squared. Okay? If this is the case, now let's do some manipulation here. From here, we can have that P over V, when I divide through, if I divide this thing by V, I have 1 over V, V takes care of V, and I divide this by V. I'm going to have P over V equal to M over the square root of 1 minus V squared over C squared. I hope this is clear. Okay? Here too, if I divide both sides by C squared, I'm going to have E over C squared is equal to M over 1 minus V squared over C squared. Okay, so you see this is equal to this. So if this is equal to this, then it means that P over V is equal to what? E over C squared. Okay, now let me do some manipulation here also. You know that P over V is equal to E over C dot C. That's C times C, right? I can bring this, I can cross multiply just this two, so that I have PC over V equal to E over C. I hope this makes sense. Okay, if that's the case, then I can also exchange this position. It's the same either ways. So if I exchange this position, then I have C over V will be equal to what? E over PC. Does this make sense? That's momentum times speed of light. If that's the case, then I can interchange this as V over C. Definitely, I will also reciprocate this PC over E. Does this make sense? Okay, if this is the case, you know that this VC is what we have inside this equation. V over C is what we have inside this equation. Now it's squared here. So therefore, our E now becomes, recall first that E is mc squared, mc squared over 1 minus V squared over C squared. Okay, so E, so now we now have that V over C is now PC over E. So mc squared over root 1 minus PC over E, both of them are squared, so all squared. Okay, let me distribute this square so that we have E will be equal to mc squared over root 1 minus, this is mc, okay, yes, P squared C squared over E squared. Okay, if this be the case, then we can square both sides so that we can eliminate this square root and of course collect E's together. Okay, so if that is the case, then by squaring both sides, we're going to have E squared on this side. E squared will be equal to M. Now, M is squared now. C is now, C squared before square will become C raised to the power 4. All over. By the time you square this guy will go away and we have 1 minus p squared c squared over e. It has taken care of the e squared. If it has taken care of the square root, this square has taken care of the square root below. So you now cross multiply. By the time you cross multiply, you're going to have m squared c to the fourth equal to e into bracket 1 minus p squared c squared over e squared. Okay? So if this be the case, then we have m squared c to the fourth equal to e times 1 is, no, wait, e squared, I'm sorry, there's e squared, so when we cross multiply it has to be e squared, so e squared minus e squared times d is here, e squared times p squared c squared over e squared, so e squared takes care of e squared, so we have m squared c to the fourth equal to e squared minus p squared c squared. Therefore e squared, when you bring this guy here, will be equal to m squared c to the fourth plus p squared c squared. So this is the formula for total energy of a moving body in relativity, in relativistic perspective, in special relativity, total energy. All right, this will be the end of the video for today. I hope you enjoyed it and you were able to learn how to derive all the equations. I hope you enjoyed and knew how to derive all the equations. If you have any comments or questions or concerns, you can let me know. And also, you can reach me on the WhatsApp number +2349021416307. If you need me to snap all of this notes and send it to you, some people prefer to want to study it again. Is that okay? So, and of course, if there's anything you don't understand, I want me to solve questions using these formulas, just put them in the comment section. I'm going to attend to it. Do want to subscribe to the channel, please. If you have not, subscribe, share the video with your friends that need it. Is that okay? God bless you as you do so. All right.